Hello there. So let's turn to spectroscopy for the semester. If we switch to mass spectroscopy, we take a sample and heat it up to vaporize it, then pass it through a chamber where it's bombarded with electrons to ionize it, and then accelerated through the magnetic sector, where these fragments of molecule break up and are deflected according to the mass and charge. Lighter fragments are deflected further than heavier fragments. All this information reaches the detector and then is amplified and recorded on a chart. There's also a vacuum pumping through the system to make sure that there's no samples left that don't make it to the analyzer. So our spectrum shows the mass to charge ratio. Thankfully, most fragments have a charge of 1 plus, and so the mass divided by the charge is still equal to the mass. And we have the relative abundance on the y-axis. This is based on the base peak, which is the most abundant fragment found, and everything else in the relative percentage is based on the abundance of that most commonly seen fragment. So it's given a value of 100%, and everything else is compared to the relative abundance of that base fragment. The very last peak we see in the spectra is usually the molar mass peak, or what we call the molecular ion peak. We'll sometimes see an M+1 peak or an M+2 peak if we get slightly heavier isotopes turning up in some of the sample, like maybe carbon-13 in a molecule instead of carbon-12. Sometimes the molecular ion peak doesn't appear, but in our examples, I would always tell you if that was the case. So if we take an example like a ketone here, it's put through the analyzer and starts to break up. As it starts to break up, it breaks up into these fragments. Some of the fragments will have a charge and be known as cations, but some of the fragments, as they break up, just give unpaired electrons and are therefore radicals. Molecules which have atoms with unpaired electrons are known as radicals. So collectively, both things can happen. Sometimes the molecule breaks up to give a cation, sometimes breaks up to give a radical. So we talk collectively about these cation radicals which are being produced. It's only the cations which are being detected by the machine, and the vacuum sucks out any radicals which would endanger the machine being filled up with unwanted sample. So when the chemical bonds fragment and break, it's normally the bonds which are polarized or bonds next to polar bonds which break. Classic example here, a bond, a carbon to carbon bond, just adjacent to the functional group, that polar carbon to oxygen bond in the molecule. So a polar covalent carbon to oxygen bond. And then the bonds around those polar bonds are themselves polarized slightly as the electrons are drawn towards the electron deficient carbon. So polar bonds break and bonds close by to polar bonds break. The carbon to carbon bond here breaks next. This is what we call alpha cleavage as the bond breaks. And then finally, the alpha bond on the other side also breaks to give us our last fragment at 29 units. If we look at the 2-methylbutane, again we can see our peaks according to the mass divided by the charge. Again, most of the peaks will be for a charge of just 1 plus, which is therefore giving us a value equal to the original mass for that fragment. As the molecule fragments, again we are showing preference to more stable cations as it breaks up. For example, if we lose this methyl group, we produce a secondary carbocation. A secondary carbocation is more stable than a primary carbocation. Molecule breaks up further, breaking the carbon-to-carbon bond next here to give us this ethyl group again. The molecule can break up in different ways, of course. And so we could break the carbon-to-carbon bond here, which would again give us a secondary carbocation, more stable than a primary carbocation. The more substituted the carbocation, the more stable it is, and the more likely we're going to see a peak in the mass spectroscopy. Look at one more, an ether. Again, the polar covalent bonds and bonds adjacent to the polar covalent bonds are the ones most likely to break. So we can see that alpha bond cleavage on the left-hand side, breaking the first carbon-to-carbon bond, giving us a peak at 29. We can see the molecule breaking up on the other side through that polar oxygen to carbon bond to give us two fragments at 45 and 57. We could see the carbon to carbon bond on the other side breaking to give us the other half of that original fragment. So peak at 87. This fragment can break up further as we lose that oxygen to carbon bond. And then finally, we get alpha bond cleavage on the other side, the first carbon to carbon bond on this side, again giving us two fragments that we see in the mass spectroscopy at 59 and 43. So the molecule can fragment and break up multiple times, and it can also break up in different ways. We also get a lot of information about halogens from mass spectroscopy. A good example of this is bromine. Bromine, of course, has two isotopes, one with a mass of 79 and one with a mass of 81. Oh, excuse me. Slight error there. One with a mass of 81, and it's almost a 50-50 split between these two. 50.7 compared to 49.3. So if the molecular ion peak appears, we're going to see it as a double peak, pretty much a 50-50 split, separated by 2 units. Quite often, we refer to the first of the two peaks as the molecular ion peak, and refer to the second peak with the heavier isotope as the M+2 peak. Now, sometimes we might get a 50-50 split by accident, separated by 2 units. So to be absolutely sure that you have bromine in the molecule, look for that 50-50 split separated by 2 units further to the left in the spectra, which is telling you it's not a fluke, and it's telling you that there are smaller fragments where the bromine is still attached to the molecule. Chlorine is another one that's detected easily by mass spectroscopy. Two isotopes again, one with a mass of 35 and one with a mass of 37. Their relative abundance is 75 to 25% roughly. And so the molecular ion peak is split by 2 units with a 3:1 ratio. Again, the peak from the chlorine with 35 mass is usually the one described as the molecular ion peak, and the second peak, which is just a third of the size, is described as an M+2 peak. And just as we said with bromine, to be sure that this just isn't a fluke occurring at this end of the spectra, look to see that 3:1 ratio separated by 2 units further down the spectra, where we have smaller fragments when the chlorine is still attached. We can even detect iodine in the mass spectroscopy. Two things to look out for. One is a peak at 127 for the mass of iodine itself. Once it's broken off, the iodine is often charged and often makes it to the detector. But also, one of your biggest peaks is probably exactly 127 units down from the molecular ion peak. That bond is polarized, of course, and it's very easy for the iodine to drop off first, giving the most abundant fragment seen in the spectra. Finally, look out for an odd number for the molecular ion peak. That's often a sign that nitrogen is in the molecule. Now, of course, we normally finish each hydrocarbon with a methyl group, CH3, but if one of those hydrogens is switched for an amine group, NH2, we get that hydrogen back when we add on the nitrogen, but we also get a second hydrogen from the amine group. So our hydrogen count is one more for saturation than we would normally expect. For alkanes, it would be CnH2n plus 2, but with that extra hydrogen with the amine, it's CnH2n plus 3. Of course, nitrogen in the formula as well. So an odd number for the molecular ion peak is often a sign that nitrogen is in your molecule. Of course, this can be backed up by vibrational stretches in the infrared spectroscopy.